Here we go. Let's revise. Quiet down. Quiet down. We're going to revise on your matrix skills. So you need to know how to add, subtract, and multiply matrices. Main thing is multiplication, and then hopefully I can then guide you through inverses of matrices, and that is where everything lies. Everything that you need to know lies in the inverse of matrices, what it means. Yeah. And then that will lead you to understand what you're meant to do for 2F, 2G. They're all calculator work, but I want to teach you the sort of manual way as well, because some exams will require you to do it manually. They say that you don't need to anymore, but I think it's still a helpful skill so that you could answer the questions either with a calculator. Yeah? All right, so before we get there, let's go with some basic skills. So, last year in Specialists, you would have learnt matrix dimensions. Yeah, anyone remember what a matrix dimension is? What was it again? What's matrix? Will. Size of a matrix, which you can have. Good, something by something. So when I say 3 by 2 matrix, what does that mean? What does 3 represent, and what does the 2 represent? Can I please yes, Anna? Good. This means I've got 3 rows and 2 columns. So this represents rows. This represents columns. So if you were to write it, it'd be A, B, C, 3 rows and 2 columns. That's a 3 by 2 matrix. Okay? So you got your matrix dimensions, m by n. M means rows, n means columns. Then you have to learn what we call addition and subtraction of matrices. That was the first exercise that you did in Specialist. So how do you add and subtract matrices? The first step is you needed to have the same dimensions. Why is that? And what does it mean by saying same dimensions? It means same row, same columns. Okay, so 3 by 3, 2 by 2, or if it's 3 by 2, then the other one has to be a 3 by 2 as well. So they have to have the same dimensions. Now when you add them, let's say I give you 3, 1, 2, 3, and I want you to add with 3, 4, 5, 6. What would this become? Can I please have, let's go with Aaron. What would this give me? How do you add matrices again? Okay, that's good. That's why we're revising. Trent? Okay, so you got 6, 6, 6, 9. Now. Magic. I just came up with those numbers. I don't know how it came out. Alright, so. Now, how do you add and subtract matrices again? The row by column gives you a coordinate or like positioning in the matrix. When you add them, you're adding position by position. So for example, this first 3 in the matrix, we call that your row 1. So row 1 by column 1. So this 3 here is a row 1, column 1. So when you add them, they have to be the same matrix because you're going to be adding all the row 1s and column 1s together. And a way to think about how it works logically, if I said this to you, I said, this is the math scores. This is the percentage scores, right? And this is for quadratics, cubics, and calculus. I'll do calculus there, yeah? And you got 4%, 10%, and 20%, right? If we're now adding on with another matrix, where I now write 5 for your quadratic, your second, your retest, now you get a 5%, and then you get 20%, and you get 25%. Okay? When we're adding it together, your total percentage so far after the retest, you would say, well, for quadratics, it would be 4 plus 5. You wouldn't do 4 plus 20, because that was a different test. Yeah? It's the same thing with your matrices over here. It's what this row 1 and column 1 represents. Okay, this could be term 1, your first test. Okay, next year, term 1, first test. So when you add them together, term 1, first test, overall, what did you get? Yeah, so that's why you have to add it by their entries, add them by their positions. So in our case here, you'd say 4 plus 5, 10 plus 20, 20 plus 25. But they have to be the same dimensions for you to add. Otherwise, it doesn't make sense. How do you add something that doesn't exist? Does that make sense on adding, subtracting matrices? Yeah? Second thing then leads to, so once you know how to add, subtract, you need to add or subtract by positioning. Then the second thing is multiplication of matrices. This is where it gets tricky, or most students will have forgotten. How do you multiply matrices again? So let's say I gave you 3, 2, 1, 1 by 2, 2. Does that even work? Yes. All right. Now there was a rule. In order for you to multiply matrices against something, you have to look at something before it works. What are you looking for, Ben? What order?
Oh, the dimensions.
What about the dimensions?
Like the amount of columns and rows.
Okay, so in this case here, the first one I have,
2 by 2.
I have a 2 by 2 matrix, and the second one I have
2 by 1.
2 by 1. So what, as you just said, we need to make sure the first thing you need in order to multiply matrices is you need the column of the first matrix to be equivalent to the row of the second matrix. If these two are equal, then your result matrix, the resulting matrix, will be what again? What was the tip? Give it 2 outer sides. So your resulting matrix will end up being a 2 by 1. Okay, so that's the overall idea. So what I know is when I multiply that, my ending matrix should end up being, I'm going to write it over here in blue, it should end up being a 2 by 1 because I've got a 2 by 1. Now, the question is, how do you get that answer? Okay, so how do you multiply matrix again? Anyone know? Mazen?
So, times the top left number. 2 by 2.
Yep, so it'll be 3
times the top 2. So like it's like
yeah, no.
3 times 2.
Yeah, 3 times 2 plus
1 times
plus 1 times 2. Good. Now, what you're actually doing is you're doing row by column. When you're multiplying, you're taking this row 1, entire row 1, multiplied to column 1. So in this case, you're doing row 1, column 1. Okay, that gives you 3 times row 1, column 1. Okay, this one gives you row 2, column 2. Oh, sorry, row 1, column 2. And this is column 1, row 2. Or row 2, column 1. Okay, so you're multiplying to its corresponding spot. So this is row 1 by column 1. Okay, and this is row 1, column 1. So that's why you got 3 times the 2. Then you got row 1, column 2. Okay, so row 1, column 2, and this is now same thing again. This is row 2, column 1. Okay, because we want the columns and rows to be the same. So there we go. So this is how we multiply our matrices. We take this first row to multiply to the second column. Oh, sorry, first column. Okay, and then you do the same for the next one. The next one now you take out 2, 1 multiplied to. So 2 times the 2, and then plus 1 times the 2. That's why you end up with a 2 by 1. Yep.
So, like, I have to figure out especially like a train leaving the station. Like, you have the 3, 1, and it goes to the station, and you times the, yeah. Because like,
I think I see what you mean. You're saying
3, 1 goes
3, 1, 2, 1.
Yeah.
So this is 2, 2. What you're doing is this train, which I'll highlight, this train goes here and then it comes down. Is that right? So the 3 goes here and then the 1 goes here.
1 time.
All right, fair call. Yeah, that sounds like a good way to remember it. And so hence 2, 1 train station was going same way. It's coming through here, coming down. All right, cool, gotcha. All right, okay. So your answer there would give you now, if you simplify that, 3 times 2 is 6, plus 1 times 2, which gives you 8. 2 times 2 is 4, plus 2 is 6, so it's an 8 to 6, which is a 2 by 1 matrix. Okay, now, a couple of things to note, write in your notes here. A by B is not the same as B by A. Okay, so the property if you took this matrix 3, 1, 2, 1 to multiply 2, 2. If you switch that around and you write 2, 2 multiplied to 3, 1, 2, 1, it'll be a different answer. Well, in fact, it won't even work because this is a 2 by 1 and the column of the first matrix does not match the row of the second matrix, so you can't multiply that. Okay? So AB does not equal to BA, unlike our normal numbers multiplication. 3 by 2 is the same as 2 by 3. But in this case, matrix A by matrix B is not the same as matrix B by matrix A. That's the first one. Yeah? Can only multiply if the column of matrix A is equal to the row of matrix B. That's what Ben was saying. So matrix A, column of matrix A is equal to the row of matrix B. Okay? And then this is how multiplying position R1, column 1, and that's what I was showing just now. Okay, so that's your matrix multiplication, which we'll do more practices so you get a feel of it. That's what exercise 2E is about. And the last thing, this is where everything ties up together. So matrix dimensions, addition, subtraction, multiplication is just revision. What you need to remember or understand is what matrix inverses actually do. What is the point of having it? What the determinant actually determines. Okay? And here we go. So I want you to write this down, and these are the two things we're going to have to pay attention to. Inverse matrix is like the opposite operation of matrix multiplication. The problem with that is we're so used to, if you can times matrices, we would think that means you can divide matrices. No, we don't have a division for matrices. The only inverse we have is what we call the inverse matrix. And I'll show that to you later. But right now, this is what I need you to be able to do. Just to revise again. Matrix dimensions, add, subtract, multiply, find inverses, but this second line here, inverse will exist if the determinant of the matrix does not equal 0. So I want to understand what that means. And what does it mean when determinant of matrix A doesn't equal 0? What does it mean? What are you visualizing? What is the matrix telling you? And how are you going to apply that? That's what I want to teach for chapter 2. Okay? It's kind of like your derivatives. Understanding derivative gives you the gradient of a tangent line at one point. Same thing with this one. The inverse of a matrix, what does it tell you? What does it mean? Okay? So if you had to copy, that's what I want you to copy there. Okay? All right, here we go. Next one. Oh, just in case, how do you find the determinant? AD minus BC. Just copy that for now. When we get there, it'll make more sense. Okay, so we're just going to copy that for now. Determinant of A is equal to A times D minus BC. And once I show you the proof, you'll understand why that's true. Determinant of why it's even called determinant. It's very similar to your discriminant from quadratics. Without the quadratic formula, you don't have a discriminant. Without the inverse formula, you will not have the determinant. That's how it sort of works. Okay? We all good? All right, next one. Here we go. Let's do some examples. Here we go. Let's do the first one. If I were to add 2, 4, 1, 3 by, so 2 by 2 matrix by another 2 by 2 matrix, what will I get, Daja? 0.
3, 5, 6.
Good. 2 plus negative 2, 4 plus negative 1, 1 plus 4, and 3 plus 3. Yeah? So here we go. Oh. I'm just doing it right there. Okay? Next one. Now, when we're multiplying, this is multiplication of matrices. So add and subtract the same. You're just going to have them have the same dimensions. Once they have the same dimensions, you can add, subtract according to its positions. Now, I want to multiply this. Can I multiply this matrix is the first question. You got a 2 by 2. So I write it down. You got a 2 by 2, and you're multiplying by what kind of dimension do I have here? 2 by 3. So this is a 2 by 3 matrix. So yes, the column of the first one is the same as the row of the second. So yes, we can multiply it. And that means the answer will end up being a 2 by 3 matrix. Okay, so how do we do this? Same thing again. So you can go with Trent's sort of train schedule. Row 1 multiply to column 1. That will give you row 1, column 1 answer. If you take row 1 again and you multiply to column 2, then you get row 1, column 2. And then if you multiply row 1 with column 3, then you get row 1, column 3 answer. Okay? So that gives you these 3 answers up here. So I'm going to show you how it looks. Let's just follow that idea. Here we go. First one, it's 2 by 3. We're going to do the train 2 by 4. So row 1, this is row 1, multiplied to column 1. Here's my answer. I know the answer is going to be a 2 by 3 matrix. So I'm taking 2 times the negative 2, which is here. 2 times negative 2. And then 4 times the 4. And that gives me row 1, column 1 answer. Whatever that answer is row 1, column 1. Yeah? So that's what I'm doing there. So we just simplify that. And we did the same for the next few. Row 1 times column 2. So that becomes 2 times negative 1, 4 times 3. I get the answer for row 1, column 2. If I do row 1, column 3, so 2 by 2 and the 2, negative 1, I get row 1, column 3. Okay, so it's all about getting those values. So if I write it all down now, this is what it looks like. So how does it work? Let's think about it. 2 times negative 2 is negative 4. Negative 4 plus 16. That's how I get 12. The next row 1, column 2, you can see 2 times negative 1, which is negative 2, plus 12, gives you 10. That makes sense. Row 1, column 3, 2 by 2 is 4, plus 4 times negative 1 is negative 4. That gives you 4 minus 4, 0. So that's your row 1. Row 1 by column 1, row 1 by column 2, row 1 by column 3 gives you the answers for the positionings. Okay, and then you do the same thing for row 2. Row 2, you have 1 and 3, so when you multiply it, it will be 1 to the negative 2, 3 to the 4. That's what I got here. 1 by negative 2, 3 by 4. Negative 2 plus 12, 10. Okay, so that row 2, column 1 gives you the answer for row 2, column 1. That gives you the answer when you multiply them. Okay? How do we feel with the matrix multiplication? Was that an okay revision? Feel a bit better with that? That's what exercise 2E is about. Pick out the questions and try to do them. Yep.
So it's like with the 2 by 2.
Yep.
It's like the train paths and it goes sideways, right?
Yeah. Yeah. Exactly. Yeah. Exactly that. Okay. Okay. Now, once you know how to add, subtract, multiply, the reason why you need inverses is so that you can solve. Just like algebra, the reason why you learn inverse operations is so that you can solve for x. Now this x in this case here represents a matrix that you don't know. So to find this matrix, your goal is to find matrix x. That's what you want to know. You know that matrix A is given by this matrix. You know this is going to equal to matrix B, which is this. So you're going to follow down the formula here. If you think about it, this just means 2 times matrix A, whatever matrix A is. I'm going to double everything in there. Add matrix X, and it gives me matrix B. Now, if you want to find matrix X, naturally, you'd say minus 2 matrix, whatever this is, and then minus 2 times the matrix A. Does that make sense what I'm doing? So I'm just writing out the equation. Whoops. I'll just do it again in red, actually. Hold on a second. So what we can say here is if I minus 2 matrix A and minus 2 matrix A, because we know when we minus them, they should cancel out to be 0, 0, 0, 0. So it's the same thing as saying 0 matrix, right? So this matrix should equal to B, matrix B, minus double of matrix A. And that's what this line is saying. This is what I have over here. Okay, so this is my B minus 2 times A. Alright? Now, because this is a scalar product, or if you have a constant, you've got number 2, you don't have to do matrix multiplication. In this case here, you're doubling every coordinate in here. In this case here, 2 times 3, 2 times 2, 2 times negative 1 will give you the next line. And you get, let me just fix that. That becomes 2 times 3, 2 times 2, 2 times negative 1, 2 times 1. So that's what all of this represents so far. Okay? But then you're minusing, you're doing 0 minus 6. So 0 minus 6 gives you negative 6. You got negative 4 minus 2 times the 2, which gives you negative 8. And then if you follow the same concept, you do negative 2 minus negative 2 times negative 2 is positive 2. So negative 2 minus 2, sorry, plus 2 is 0. And then finally, if you're going to follow on the same idea again, we're going to take 8. So 8 minus double of 1, which is 2. So 8 minus 2 is 6. Okay, so that will tell me the matrix X by inverse operations there. Right? But all I've done so far in terms of inverse operations is instead of adding, I'm subtracting. And we can do that. We know the opposite of adding a matrix is subtracting a matrix. Where it gets tricky is when you have matrix A times matrix X, you need to do the inverse. Okay? So doing the inverse, we don't have division, we only got inverse matrix. Now the question is, what is the inverse matrix? How do you find the inverse matrix? Okay? Anyone remember that? Oh, really? Let's go, Ben.
Oh, so it's 1 over the determinant, which is AD minus BC,
Yes.
times the matrix, which is normally A, B, C, D, but it's D, negative B, negative C, A.
Like that?
Yeah.
Good. Everyone copy that down. This is your inverse matrix formula. It is a formula, and I'm going to show you the formula to it. And that's the key to understanding what it means when you do the inverse. And it might take another session to do that. What time do we finish? No, I can go through that. I think it'll just be a bit of a smack in the face, but you've got the long weekend to sort of try to get into it. Yeah? I am going to do it. So I know I can give you the formula, and I know you can do Exercise2E from here. What I don't like about that is you want to understand what this all means. Yeah? So I'm going to guide you through what this whole formula means. It's about that. That's what chapter 2 is all about. Okay, so that's your inverse formula. Normally when we write a matrix A, we denote it as A, B, C, D. So when you do the inverse, this is the formula where A and D switches, and it becomes negative B and negative C. And I'll show you why. Okay, I'll show you why that's the case. But here we go. Just copy the formula, so that at least you can do the exercise even if you don't understand what I'm saying after the proof. Okay? So inverse is 1 over AD minus BC multiplied to D negative B negative C A. Okay? That's the inverse of A, or inverse formula. Here we go. So, here's the problem. We don't have division for matrices. So in this case here, we can do the inverse matrix, and you can add matrices and subtract matrices of the same dimensions. So if that's B, to get rid of it, I can minus B and it becomes 0, 0, 0. And I have minus B on the right-hand side. So that's okay. The problem is here. A times X, I need to remove A. Now the only way to remove A but keep X, okay, because I don't want to lose the X either as well. So I need to multiply something, or somehow I get rid of this A, so that it becomes 1. Because if I get it 1, then 1 times X would just give me X. That's the goal. Now, last year in Specialists, they introduced an idea to get 1, the equivalent of 1 for a matrix, is what we call the letter I. I stands for the identity matrix. And what that really just means, it's a 1, 0, 0, 1. You multiply this to any 2 by 2 matrix of itself, will end up being the same. So if I did 1, 0, 0, 1 multiplied to, let's say, 2, 1, 3, 4, it should end up being the same. So let's do the row 1, column 1 thing, yeah? Row 1, 1 times a 2 So 1 times 2 plus 0 times 4. Okay, and what you can see is already 1 times 2 is 2 plus 0 times 4 is 2, and that's the same. If you follow on the same thing again, 1 times the 1 gives you 1, and then 0 times the 4. Oh, what did I do there? Which is 0 times 4, which is 0, and it ends up being 1 again. So you get the same value. So if you actually try to expand 1, 0, 0, 1, and you try to multiply it by 2, 3, 1, 4, you'll find that it becomes 2, 1, 3, 4 as well. And that's the important part. So if you try doing the matrix multiplication, 1 by 2 plus 0 by 3, it ends up being 2. 1 by 1 is 1, 0 by 4, again, equal 1. 0 by 2 is 0, and then 1 by 3 is 3. So you get 3. And finally, 0 by 1 is 0, and then 1 by 4 is 4. Okay? So this is what we call the identity matrix, and that's great. So what's the question? And that's really important here. This is what you want. You've got a matrix A that you don't know, so we call it A, B, C, D. What you want is something to multiply to A, so something multiplied to A, something, okay? Something multiplied to A to give you the identity matrix. Because if you get an identity matrix, that times X should give you the X that you want, right? The question is, what should this be? And that's where the inverse comes in. Your inverse formula, if you times that to A, it will remove everything and makes it 1, 0, 1, or 1, 0, 0, 1. Identity matrix. That's what it's doing. Okay? So, this is what we want. We want something to multiply to A to give you the identity matrix. And this is the formula they came up with. After doing a proof, that's the formula that I asked you to copy down, right? Now I'm going to show you in the next slide how that comes about. Because once you understand how it comes about, it makes sense why they say inverse does not exist if the determinant is not equal to 0. Okay? So inverse does exist, sorry, I mean if the determinant is not equal to 0. Okay, so inverse will exist. So the question is, what does the inverse mean? Right? So here we go. Actually, I'll go to the proof. This is just showing you how to do it. You can watch this PowerPoint at home, and you'll see how you can use the inverse matrix to get the answer. Okay? Now, what are we really doing? Is this the proof? No, not the proof yet. No. Oh, okay. I get it right back here. All right. Here we go. In this example, I try to illustrate the idea of what does it mean when you take matrix A times matrix X equals matrix B. In order to find matrix X, you have to remove A. Now we know that if you multiply both sides by the inverse, the nice thing is A inverse times A should give you the identity matrix. These two multiplied together should give you identity matrix. Identity matrix times X should give you X. Now to find X, you're just meant to use the formula 1 over, yep. Yeah, you can. Yeah, you don't have to write this. I'm just writing it so you get it. Yeah. Okay, so using the formula that you had from the previous slide, A inverse. To find A inverse, we said it was equal to 1 over AD minus BC times DA. Oh, whoa. Oh my God. What happened? Times DA minus B minus C, right? That's how I got this one here. So 2 times 1, A times D minus 2 times -1. That's how I got 1 on 4, right? Multiply those two and you get this answer. Once you go through them, you multiply them and you get your answer -3, 1. The question is, what does -3, 1 represent? What does it mean? So what I try to show here is when you write, this is matrix A and this is matrix X, we call it XY, equals to matrix B, which is this line over here, okay? What you're actually doing is you're saying, if you actually multiply this matrix out, oh, I don't know why isn't it rubbing? Okay. If you multiply the matrix out, have a look at what's happening. You're actually writing 2 times the X, 2X, plus 2 times the y is equal to negative 4. That's what you're getting. You're getting a linear equation for the first row. The second one, negative 1 times x plus 1 times y equals to 4. You get another linear equation. Now, if I asked you to do simultaneous equations here, okay, if you simultaneous equations here, what you're going to get, oh, it doesn't rub anymore. All right. What you're going to get here is if you actually solve for simultaneous equations, you actually end up getting here. Now, what do you remember again? When you use simultaneous equations, what are you actually solving for again? What are you finding? When I find x and y, what am I finding? Yeah, it's an intersection of two lines. When you actually use simultaneous equation elimination method, what you're doing here is you've got two straight lines, and you're trying to find the x coordinate of the intersection. That's what it is. And if you want to find the y coordinate, you sub x back in, and you find the y coordinate. It just tells you the point of intersection. So, this matrix method, when you do the inverse and solve for x, what you're actually doing is you find the point of intersection, and that's key. That's key to understanding what chapter 2 is all about. Yeah?
If you can just use simultaneous equations, why do you need to know?
That's a very good question, because at this point in year 9, year 10, you guys learned how to do simultaneous equations, 2 equations, right? When you get to uni, the first step that you're going to be learning is first year mathematics is you're going to learn how to simultaneous equations of 4 to 5 onwards. And you can do this by hand, and it's much quicker to do by inverse matrices. And they have an inverse matrix formula for 3 by 3. We don't learn it in year 11 and 12. I've forgotten it now. But there is a method, and you'll know how to do it 3 by 3, 4 by 4, 5 by 5, meaning you can do 5 equations by 5 unknowns. And you can just do it systematically. Instead of, if I gave you 5 simultaneous equations now, it would have been a pain to do, just trying to substitute. Yeah, exactly. It would have been a really intense work. Matrices simplify that. That's why you're learning it. Yeah. Okay, but for our case in year 11, year 12, you're only going to learn how to do it for linear equations. You're not going to learn for 3 simultaneous equations or not. It's only for 2. Okay, so if it's a 3 simultaneous, you'll be using calculator. That's exercise 2G. Yeah? All right, here we go. So, this is what I want you to understand now. So this is where it's important. We just found out that when you do matrix A times matrix B equals C, the inverse matrix, it allows you to solve for the x coordinate or the y coordinate. It just tells you the point of intersection. So what does it mean if I told you that A inverse doesn't exist? Remember, you're trying to solve for intersection, but if I told you the inverse doesn't exist, that means you can't do this step. That step doesn't exist. Because if A inverse doesn't exist, that means you can't remove A. But if you can't remove A, what does that mean? You can't solve for x. If you can't solve for x, what does that mean? Yeah, they're either parallel because there's no point of intersection. The only time you don't have an intersection for 2 lines is either they're parallel or if they're the same line. Now, if they're the same line, why is it not? Why doesn't it have an answer? That's what we were talking about last year. Yeah, infinite many solutions. Why? Because you don't have one answer. See, if I gave you this, if I told you to solve, I want you to solve for y equals 3x, and I want you to simultaneous this. What do you get? What would the answer be if I told you, work out what x and y for me right now? You get 0. You don't get an answer for x, and neither do you get an answer for y. Why is that? Technically, 3x they're both the same line. You should have infinitely many points that are the same. When x is 1, y is 3. When x is 1, y is 3, they're all the same. There are infinitely many intersections if they're the same line. But if you try to solve it algebraically, you don't get anything. You don't get an answer. So it's the same thing with matrix inverses. If the only time that you don't get an answer or you can't get an inverse is when it's the same line or the parallel. Because if they're parallel, there is no intersection. But if they're the same, then you have too many intersections. There's not even one. We just want to know one point of intersection. And that's 2 straight lines. 2 straight lines with different gradients will always have an intersection. Yeah? Does that make sense so far? Because that's the only part of chapter 2. If you understood that, you can just walk out and go, okay, I got it. That's all you had to do. You just had to understand the inverse the inverse matrix allows you to find whether there is a point of intersection. Okay? Now the question is, well, when does the inverse not exist then? So when can't you have an inverse? Well, if you have a look at this, what's the restriction in this equation? AD minus BC, why? Why, Alessia? It can't be 0. Because if you have AD minus BC being 0, it's undefined. That's why you wouldn't have an inverse. That's why they told you, we go all the way back to that slide. Oh, I can't be bothered going back, I can't touch it. But remember how I said inverse only exists if the determinant doesn't equal 0. That's what I was trying to say. If it doesn't equal 0, it's great. You will have an inverse. If you have an inverse, you will have a point of intersection. Okay? That's what exercise 2E or chapter 2 is all about. So exercise 2F, all you're really doing is finding when you have one intersection, so they say unique solution, which means one point of intersection. No solution, which means they're parallel, they're never going to cross, so there's no intersection. And then infinitely many solutions means you're on the same line. If it's the same line, then of course you have many points. Does that make sense? Yeah? Yes, Alessia?
How do you tell between whether they're parallel or they're...
And that's what the examiners are doing. Very good question. The only way to know. Now, what's the difference between a parallel line and the same line? What do they both have in common? Same gradient, but what's different? The line is set. That's the only difference. So if I gave you two equations right now, if I gave you y equals 3x plus 2, and I gave you y equals 3x, yes, they're parallel, but they have different y-intercepts. As soon as I have the same y-intercept, they're the same equation. So, how do you test it? You're right. Once you figure out that they have the same, or you figure out that the inverse doesn't exist, you have two possible answers. It's either a parallel line, or they're exactly the same lines. And in the exam, what they want you to do is basic year 9 maths. You simply go back to the equation, and there's only certain values that will make this equal to 0, and you'll test it. You might get 3 and negative 4. Right, I'll show you the questions when we get there. I'll do it in the next lesson. But you get 3 and negative 4. What you're meant to do is just sub it back into a linear equation and just check. Is it the same line or are they parallel? That's all you have to do, and that's how you prove it. It's normally a 3 to 4 mark question. It's a very simple concept. You just have to show that is it a parallel line or is it infinite lines? And the only way to know that is if you check the inverses. How do you check the inverses? Determinant. If the determinant equals 0, then you don't have an inverse. If you don't have an inverse, it's either parallel or it is the same line. That's all you're really doing. That's what chapter 2 is for your exam. That's all they're testing. Can be. There's two parts to it. So it used to be in exam 1. And exam 1 you'll do what we just discussed right now. So what you guys just asked me, how do you determine if it's parallel or infinite? They'll tell you. They'll give you a whole page. I forgot which exam it was. It might have been 2012 or 2013. But they had a whole page, and all you had to do was just go through, find the determinant as you did, write down whether the inverse exists and what does that mean, and find out when it's undefined, so AD minus BC, when will it be undefined, and then submit it in the test. And it was a whole page for 3 or 4 months. It was a simple, easy, it was a question 7 or 8 to do. That was in exam 1. But since, I think 2016 course came in, and what they're now sort of saying is you just use a calculator. So you still do the same thing, but it's in a multiple choice question. So multiple choice, you just have to show is it infinitely many or like unique or no solutions. But they didn't say that they're going to remove the idea from exam 1. So you might get it from exam 1, but it might be a 2 or 3 mark question where they will say, show that's infinitely many solutions. That's what you might have to do. Okay? But in the past, yes, it used to be just the exam 1 or exam 2 multiple choice. I haven't seen it in extended response, maybe because I haven't checked all of them, but it's always been in exam 1 or multiple choice. Okay, so that's 2E, 2F is the 2 skills that you really need. That's why I said I can teach chapter 2 all in that one lesson, because that's what you need to understand. It's all chapter 2, and you can move on. Yeah? But anyways, let's go back. Do I have enough time? No, I don't have enough time, but this page here can watch that in your own time, but I was just showing the proof to why you have 1 over AD minus BC. This is the proof to getting the inverse. And really, all you're doing is you're changing a linear equation. You're changing the linear equation to matrix form. So you're saying matrix A times matrix B equals to the identity matrices. That's what we wanted. We wanted, remember at the start, this is what we wanted. We wanted, this is A, and we wanted something to multiply to it. Well, in this case, it's more like this way. A multiplied to something, it had to equal to I. That's what we wanted. And so in this case here, they said, all right, well, let's call A, B, C, D. Let's call A inverse X, Y, U, V. We know the result is 1, 0, 0, 1. If you expand it, multiply these two matrices together, you get A times X, so row 1 by column 1, A times X plus B times U. A times Y plus B times V. You can do that, you get your 4 entries. Yeah? Now they're all equal to, this one equals 1, that equals 0, this equals 0, this equals 1. So because of that, you get 4 different equations with 4 and 2 unknowns that you can solve for. And that's what they're doing. So all I did was AX plus BU, which is the first line, equals 1. And I said that equals 0, that equals 0, that equals 1. And all I did was I took all the AX plus BU with CX plus DU. I got the X's and U's together. Linear equation, this is exercise 2B, literal equations. So you can do simultaneous equations to solve this. I times it by D, and I times this by B, so that I get BDU and BDU. Subtract it, and what you find is I end up getting D over AD minus BC. Now you do that same step for X, for Y, for U, for V, and it ends up being this. And they all have a common factor of 1 over AD minus BC. That's why you take that out. It's common factor, and that's what happens. That's where the proof comes in. And that's why they say, all right, so in order to get 1, 0, 0, 1, X, Y, U, V has to be that, this. That's all it is. And that's why this is called the inverse matrix. But that's how they started. They said, all right, well, we don't know what this is. Let's just call it X, Y, U, V. And they just carried through. And that's how they got this formula. And so now, I said I could just teach you to say, learn that, but I wanted you to sort of understand you're just finding intersection of 2 lines. So unique solution means one intersection, no solutions mean they're parallel, hence no intersections, and infinitely many means they have to be the same lines. Exercise 2F allows you to practice that, whatever I just told you, that theory, and then that's what we'll do next session. Okay? But 2E is just revision of all the skills you learned in specialists for matrices. All right, we'll call that a day, but that is it. We'll do more practices on 2F, and that's really chapter 2. That's really chapter 2. You get that, you can move on to the next one and forget about everything else. You can just kind of like,
Yeah, that's what happened.
yeah. Thank you.